And we start with a presentation by Kirill Grishin, who will talk about observing, calibrating, and reducing near-infrared imaging mosaics.
Hello, I'm Kirill Grishin, PhD student at the University of Paris, and I'm also doing some research at Moscow State University. And today I want to tell you about our recent experience that we had with observing and reducing imaging mosaics in infrared with MMIRS spectrograph on MMT observatory. And first of all, let's talk about main differences between obtaining images in optical bands and infrared bands. The main problem is that infrared detectors have a lot of imperfections and there are significant variations of sensitivity on small time scales, and also sensitivity depends highly on spectral content of light. The other problem comes from the high night sky background level, so you get very close to the saturation level even with 20 seconds of exposure time. The solution for the first problem is dithering. So you shift your image, you obtain a sequence of randomly shifted images and then analyze them one by one. The solution for the second problem is splitting whole exposures, long exposure into the smallest ones, and then also analyze them one by one. But when you need to observe extended objects, you need to obtain imaging data for several fields. And this is what I will be talking about in my talk. And here are some science cases of imaging mosaics in infrared, and you can do it for extended nebulas, for globular clusters, for even open clusters, for star, I would say star clusters, and for many other objects that fills a significant part of field of view, or even the fully fills field of view, or field of instrumental view. But in my talk, I will focus more on the obtaining in mosaics for galaxy clusters, and I will show you what we did for Coma cluster. And as I said, in infrared bands, you need to do dithering. And dithering procedure, it's better to say that here is a shifting telescope, is a low-cost procedure for telescope time, because it takes much less time than, for example, changing positional angle of the instrument or the telescope. And this is the main reason why it's better to do joint dithering catalog for different nearby fields instead of doing dithering patterns for each field separately. But at the same time, if you plan to observe different fields at different positional angles, it's better to do fully separately, because, as I said, it takes a lot of time to change telescope positional angle. And this is what we did in our project. I want to say a little bit about our observational program, because we did infrared imaging follow-up campaign for multi-object spectroscopy data obtained with a newly designed and commissioned binary spectrograph on MMT observatory. And on this image, you can see Coma cluster rotated by 90 degrees. And green squares shows their positions and footprints of MMIRS fields of view. And here you can see that we use only two position angles, 0 degree and -20 degrees. And we observe fields with different position angles separately in different nights. But fields with the same position angles are joined into a single dithering catalog. After we have obtained all the data, we need to reduce it. And we used ordinary standard MMIRS pipeline for this purpose, which includes such procedures like dark subtraction, flat fielding procedure, and also doing shifts in order to correct dithering pattern. But the last part of data reduction for infrared images is the most interesting part. This is the sky subtraction. There are two standard ways how to do sky subtraction for near-infrared imaging. The first way is when you use the same science frames to build the sky model for image and then subtract it from the science image during the reduction process. But it works very good for compact objects like stars, even if you have a lot of them in the field. But for our purposes, when you have a lot of galaxies, because we are working in the galaxy cluster, we are obtaining data for galaxy clusters, this algorithm leaves a lot of black holes, black rings around extended objects, extended galaxies, and this fully erases information information about the outer low surface brightness parts of the galaxies, and for our purposes, this is not the case because we need to know about extended dwarf elliptical galaxies or outer diffuse galaxies. We need to know about their outer parts. The second approach. The main idea of second approach is to use science images other from images you are reducing to construct a sky background model, and it works pretty well because it doesn't produce this over subtraction artifacts like black holes or black rings, but at the same time it leaves a gradient, global pattern of sky background on the reduced image. And on the second row, you can see that there is a global gradient. Thank you. But this global gradient can be subtracted using global sky background subtraction algorithm. But it also produces black rings and black holes around the galaxies. But we did a different thing for this data set. We subtracted background from each frame in a stack by masking galaxies and other sources from the median image, from the median coordinate field, and by fitting the residuals, which is night sky background difference by low-order polynomial. The main idea is to extract the gradient, which will vary very fast on the very small time scale. So here you can see the sequence for 1 hour image with 10 seconds between each frame. And this is the reason why we need to subtract background from each frame in a stack. And after this procedure, we applied this method to each frame in a stack. We collated all images in a stack, and here you can see how sky correction improves the global pattern of sky background. Okay, we have did some data reduction, but for doing imaging mosaics, we need to have accurate astrometric solution for our images. But the WCS, the initial WCS in reduced images comes from the telescope control system, and it is not accurate at all. It contains shifts and some rotation. And what we did, we did Lemberg Marquardt minimization for determination of best values of WCS parameters. And after this procedure, the last part needed for mosaic construction is the zeropoint determination. We need to do a fax calibration. For these purposes, You simply match the catalog of sources on your frame with the reference catalog, and after this you do regression best fit minimization, where you derive the 0-point value. And when you have calibrated our astrometry part and both astrometry part and both photometry part for your image, you can build your mosaic. But for such a huge fields of view, for such huge mosaics, using the bits file is not a good idea, because you need to deal with, when you are trying to analyze some objects, some maybe small galaxies, some stars, you need to deal with the whole image, with the whole data set of 12 gigabytes. And the best way to overcome this difficulty is to use heaps survey, which can be viewed in Aladin. And this is what exactly we did. We put our data into heaps survey, progressive survey, and you can analyze it now from Aladin Lite and from Aladin desktop. And here I just put some main points of my talk, some tips and tricks that can be used when you are obtaining imaging mosaics. And I hope that it will be useful for your research, and you'll be able to build another nice data sets, infrared imaging data sets for your targets. Thank you.
Thank you very much, Kirill, for that talk. I see no questions on the Discord channel, but are there any questions in this room? I don't see any either, so thank you very much indeed.